Hello and welcome to DBForge Studio for PostgreSQL tutorial. DBForge Studio for PostgreSQL comes with a feature called the Query Profiler. It helps DBAs and developers troubleshoot slow-running queries to optimize performance. In this video, we will see how the Query Profiler works. The Query Profiler has a graphical interface that shows each step of a Postgres query's execution plan. The profiler displays the plan in a separate tab of the SQL document. This makes it easy to switch between the query and its plan without opening a new window. The query profiling information includes the date and time of the query, the total execution time and planning time, a plan tree, a graphical plan diagram, the top operations within the query plan, and an XML version of the query plan. As we will see, the plan diagram has an extensive set of information that helps you identify potential bottlenecks. When the profiler is active, it saves the query plan every time the query runs. This allows you to compare the query's performance before and after you have made any optimization. Also, you can get a query's plan without even running it. This can save a lot of time when you are analyzing and troubleshooting queries that take a long time to run. In our example, we are using a freely available sample database called DVD Rental. It has several tables, views, functions, and sequences. Here, we are running a query from one of the views. This query joins three primary key tables called Film, Category, and Actors. The two foreign key tables are called Film Category and Film Actors. We are going to profile this query and see if there's anything we can tune to improve its performance. To start the Query Profiler, we can go to the Start page and then select the Query Profiler link. We can also go to the SQL menu and select the Query Profiler Mode option. For quick access, we can also click on the Query Profiler Mode button from the toolbar. We won't run the query now. Instead, we will see how PostgreSQL plans to run this query. So we go to the SQL menu and then select Generate Execution Plan and then Full. You can see the Query Profiler tab has come up in the bottom half of the screen. Let's go through it now. First, we have the navigation pane. You can see the top level node is called Query Profiler. There is a node under it that shows the time taken by the query and its date and time. In this case, this is the time PostgreSQL would have taken if it ran the query. We can see the connection string in the detailed pane, the date and time of receiving the profiling results, and the Postgres database engine version. Then we have another node under it that shows the query. The important pieces of information in this node are the execution time and the planning time. We can also see the master node type is a select node and the query's output columns. Below this node, there are four nodes at the same level. These are Plan Tree, Plan Diagram, Top Operations, and Plan XML. The plan tree shows a hierarchical representation of the query steps and the objects they access. Here we have sequential scans, hash joins, and an aggregate operation. The plan tree starts with the innermost operation running first, followed by each outer layer. As you can see, the first step of the query is a sequential scan of the category table. The plan tree also shows the startup cost and the total cost of each step and their actual rows and plan rows. We will skip the plan diagram for now and see the top operations node. This view looks similar to the plan tree, except it's ordered by query cost. As you can see, the most expensive operation in this query is the aggregate step, which is the group by clause of the query. The last node is the plan XML node. It's an XML representation of the same query plan. Now, where would you use an XML plan? Well, this is how you save your query plan for offline viewing. You can copy the XML data to a text editor and save that in a file. You can load that file in a query plan analyzer and do further analysis later. Let's now check the plan diagram. This node shows an easy-to-understand graphical query plan. You will probably spend most of your time here when troubleshooting slow-running queries. To understand a Postgres graphical query plan, you have to start from the right and move left. Each node represents a unit of work or an operation, and each node's output is an arrow. You can see the arrows are pointing from right to left. The output of a node becomes the input for the next node. Again, we can see the rightmost operation is a sequential scan of the categories table. The sequential scan produces a hash of the table. After that, a sequential scan of the film category table also produces a hash. Both hash tables are then joined. The film table is also sequentially scanned and produces a hash table. This hash table is then joined with the output of the previous join. And so the operations progress from right to left. If we hover our mouse pointer over any node, we can see several important details. For example, we can see the costs associated with every node. Cost is a representation of how much work Postgres has to do to perform a task. The higher the cost, the more expensive the operation is and the longer it takes to complete, which affects the overall query time. There are two types of costs: startup cost and total cost. Startup cost is the cost of fetching the first row, and total cost is the cost to process the node's entire operation from start to finish. We also have the list of fields returned from the node. If the node is part of a join operation, it can be either an inner or an outer node of the join. There's also the number of rows returned by the node. There are two values for the rows returned: plan rows and actual rows. Plan rows is what PostgreSQL thinks is the number of rows in that table or join. Actual rows is what it finds when running the step. Ideally, both plan and actual rows should be the same. If we hover the mouse over each table, we can compare the plan rows and the actual rows. You can see the plan rows and actual rows are the same for the film table, the film category table, the film actor table, and the actor table. However, this is different for the category table. Here, PostgreSQL thinks there are 750 rows in the table, but the actual number is 16. So this tells us something is amiss here. To troubleshoot, let's note down the total query time and the total query cost. Remember, this is a generated query plan. We haven't actually run the query. Just to be sure, let's run the query. Now the total query time has decreased significantly. That's because the query engine is running the plan from its cache. However, the query cost is the same, and the number of plan rows and the actual rows is still different for the category table. Now, PostgreSQL uses table statistics to generate its query plan. If a table's statistics are out of date, the query optimizer will choose a suboptimal query plan. To address this, you can run the analyze command. You can run analyze on the entire database or specific tables. When you run analyze, Postgres will scan the target table and update its internal statistics. So let's run the analyze command on the category table in a separate tab. Now the analysis is done, let's run our query again. You can see we have another new entry in the query profiler. The total query time has improved only slightly, but the total cost has reduced from what it was before. Also, the category table's plan rows and actual rows are now the same. Although it's a very simple example, it shows how the query profiler in dbForge Studio for PostgreSQL works and how you can use it to fine-tune query performance. To learn more about the query profiler and other great features of dbForge Studio for PostgreSQL, just download a 30 days free trial and find out how effortless database development can be.